Welcome back, networking enthusiasts. Our world is increasingly reliant on computers and the internet. Everything from our personal finances and medical records to critical infrastructure like power grids and air traffic control are controlled by computers. These days, data has incredible value. Criminals are constantly developing new ways to steal data, extort money, and disrupt operations. As cybercrimes become more sophisticated, so too must our defenses. Our computers are no longer isolated machines. They are all connected to networks, which can be a vulnerability. If one computer on a network is compromised, it can give attackers access to the entire network. In this video series, I'd like to show you a few basic steps and principles to harden your Linux system, making it more secure and less vulnerable. There are many things to consider, like keeping your system up to date, removing software and services that you don't use, using firewall to limit the surface of attack, encryption, auditing, integrity monitoring, security scans, and so on. We'll start with passwords. Passwords are the primary way to verify users' identity, and often weak passwords or lack of security measures around passwords pose a significant threat to computer system. In this video, I will show you how to ensure your users are using strong passwords, how to make sure that your users are changing passwords regularly and not reusing the same passwords over and over again. I will also show you how to minimize password brute force attacks by locking accounts after a number of unsuccessful login attempts. My name is Philip. Let's dive right in. In the most common scenario, passwords are stored as a one-way, non-reversible hash. Let's try generating an SHA-256 hash of my password. Three important things to mention. Hash function will always give you the same result for the same input. Second thing is, the result, called the hash value, is fixed size no matter the input size. And finally, the original password cannot be mathematically derived from the hashed value. The passwords are stored inside the etc shadow file that's accessible only by root user. If we look at the contents of shadow file, we'll discover username, hash algorithm, 1 is MD5, 2A is blowfish, 5 is SHA-256, 6 is SHA-512, and Y is yes script. Then there's the password salt. That's like a random string added to the password during hashing. So the same password have different hash values. If there was no salt, then identical password would always produce the same hash value. If an attacker cracked one password, they could potentially gain access to any account with the same password. Then there's the actual password hash. When a user tries to authenticate by providing a username and password, the operating system will look up the user in the shadow file, append the salt to the password, calculate the hash, and compare it against the value stored in the shadow file. Long story short, our operating system is not storing the password, but a hash value. So even if someone would gain access to your system and steal the shadow file, they still would not know your password. To get into the server, a potential attacker needs to crack the password. He does not have access to the system, and even if he did, the shadow file is owned by root. It forces the attacker to crack the password remotely by logging into the network service on the machine, such as SSH. Attacker will either go with a dictionary-based attack that is trying the most common passwords and phrases, especially as there are lists of leaked databases of passwords or common words, names, and combinations. Or attacker will use a so-called brute force attack that is trying every possible character combination within certain boundaries. Remote cracking is not as efficient as local cracking, which we'll talk about in a different video, but by using remote password cracking, it's not impossible to get in, especially if you don't secure your system properly and use weak passwords. First thing that we'll do to mitigate password cracking is limit the number of login attempts the attacker can make. To be precise, after a few failed attempts, the account will be locked out, preventing the attacker from further login attempts. For that purpose, we'll use the PAM Faillock module. First, let's create a test user with user_add command. Then let's set 123 as the password for that user and change the login shell to fish. Let's open the Faillock module configuration file. First option I'd like to enable is audit. It will log the username into the system log if the user is not found. Then let's set the number of consecutive authentication failures before the account is locked. You can set it up to a value of your choosing. Usually 3 to 5 is reasonable. Then let's set the length of interval in seconds during which those failures occur. For demo purposes, I will change it to 60 seconds, but the 5 to 15 minutes window is reasonable. Now let's set the time in seconds after which the access is re-enabled. For demo purposes, I will set it to 120 seconds, but in real-life scenario, the account should be locked for at least 10 minutes. If you set it to 0, then the account will not be automatically unlocked. You'll need to contact the administrator to unlock it. However, this opens up another type of attack, a form of denial of service, that we'll talk about in a different video. If attacker would know the login, they could lock out the account so the rightful owner won't be able to use it. A hacker goal is not always to get access to your server. Sometimes they just want to make your system unusable. That's also serious. Long story short, we did configure our PAM Faillock module to lock out an account for 2 minutes after 3 consecutive failed login attempts within 1 minute. Now, we need to enable the Faillock module. In Linux, the authentication process is handled by PAM, that stands for Pluggable Authentication Modules. It centralizes the authentication process for various applications. In PAM, there are individual modules that are called in sequence and can return success or failure. We'll open common authentication file that's included by majority of PAM configuration files dedicated for different applications like login, SSH, sudo, and so on. In other words, if we make updates here, login, SSH, switch user, sudo, cron, and other applications will be impacted. That's what we want. If we look at this file configuration structure, we'll see the module type. Auth stands for authentication, but there are other modules like account for account management, session for session management, password for password management, and so on. Then there's the control flag that defines how modules should be stacked with others. There are a few types of control flags: require, requisite, sufficient, optional. The required flag indicates that the success of this module is necessary for the authentication to succeed. If a required module fails, the user is not notified until all other modules have been checked. Requisite, this is similar to required, so it needs to be successful for authentication to be successful, but if it fails, the user is notified immediately. In other words, if a module is set to requisite and the module fails, there is no point in continuing with other modules. Then we have a sufficient flag. If such a module succeeds, the authentication is considered successful and no further modules are executed. If it fails, processing continues with the next module. Finally, there is an optional flag that indicates the module's success or failure doesn't have a significant impact on the overall authentication process. Then there's module name and module arguments. Let's quickly go over what's happening here. In the first line, system is calling the PAM Unix module, which provides standard Unix authentication that usually means checking the etc passwd file and etc shadow file. The null OK argument specifies the account with no passwords are OK. The control field success equals 1 and default equals ignore replaces the simplified required or sufficient parameters and allow for more fine-grained control. Success equals 1 means that if a module is successful, it should skip the next one line. The default case, which handles every other return value of the module, results in the line being ignored and moving on. This line has the control value of requisite, means that if it fails, the entire configuration returns a failure immediately. It also calls on the PAM deny module, which returns a failure for every call. The third line is required and calls the PAM permit module, which returns success every time. So what actually happens is the PAM Unix module is checking the password, and if it's OK, it jumps to PAM permit by skipping the line due to success equals 1. PAM permit then allows the user to log in. If, however, authentication fails, the control goes to the next line, that is PAM deny, that denies the login. Due to requisite flag, the failure is immediate and no other modules are evaluated. Finally, let's modify the authentication chain by adding our Faillock module. We'll be working with the authentication module type. Setting default die means to immediately terminate the authentication stack with a failure. Then we put the PAM Faillock module that tracks failed logins attempts for specific user and can log the account after exceeding a certain number of attempts within a time frame. Out fail option tells the module to specifically handle failed authentication attempts. In other words, if authentication fails, the control goes to our Faillock module that handles only failed authentication cases and can track and log the account if needed. Due to the die option, the authentication will fail. Now, let's handle a successful scenario. Similar to before, this applies to authentication stage. Sufficient indicates that successful execution of this module is enough to consider the overall authentication successful. Of course, PAM Unix did check the password successfully and jump to this line, so we know the password is good. Then we put the PAM Faillock module that's used for tracking failed login attempts. This time we handle successful authentication scenario. In other words, if the authentication is successful, we clear any previous failed login attempts for particular user. This essentially unlocks the account if it was previously locked due to failed attempts. Just to sum up, if the password is not correct, PAM Unix will go to PAM Faillock that tracks failed login and denies authentication. If there are multiple failures, PAM Faillock will lock the account. If the password is successful, PAM Unix will jump to PAM Faillock that will either allow the authentication and clear the counters, or if the account is locked, it will move to the next line that will deny the authentication. Let's try switching to test user with su command. I could do SSH with similar results, but for this demo I will just do switch user. Let's provide the correct password. Okay, we are in. Now let's provide the wrong password 3 times in a row. 1, 2, 3. If we look at the authentication log, we'll discover that PAM Faillock did log the account due to 3 consecutive login failures and temporarily log the account. We can execute a faillock command that will show us authentication failure record log. If we try connecting one more time with the correct password, we'll still get authentication failure as the account is locked. We can add PAM Faillock with pre-auth argument that will display if the account is locked or not. Let's try authenticating one more time. We got a message that the account is locked and how long we need to wait. Let's wait a bit and try authenticating again. Works. If we execute the faillock command, we see that failed tries have been cleared. We've increased the security of our system by introducing account locking that significantly reduces the probability of brute force password cracking. Another important security factor is password quality. Weak passwords like short words, birthdays, or dictionary terms can be easily cracked using dictionary attacks or social engineering. Moreover, if you use the same password across multiple accounts, a compromised password can give the attacker access to all your accounts. Moreover, the longer and more complex the password is, the harder and longer it takes to crack it. Linux has a built-in PAM password quality module. Let's open a common password configuration file. Here's the PAM PW quality module that makes sure the password strength is sufficient. Let's open a PW quality module configuration file and see what's inside. First, we can adjust the minimum length of password. Let's set it to 10. Then let's set the minimum number of digits in the password to 1. For that, we need to set the value to -1. I know, confusing. If we want to have at least 2 digits in the password, we would have to set it to -2, and so on. You get the drill. Let's set the minimum amount of uppercase characters to 1. Now let's set the minimum amount of lowercase characters also to 1. And finally, number of special characters to 1. There are also a few more options to play with. To sum up, from now on the system will require at least 10 characters password, having at least 1 digit, 1 upper and 1 lower and 1 special character. Let's try that. I will change the password from 123 to 1357. It's complaining that there's no uppercase character. Let's set it to 1357 uppercase A. Now it's complaining about lowercase character. Let's set it to 1357 uppercase A, lowercase a. We failed to change the password. The maximum tries defined here were exhausted. Let's try to set the password to 1357, uppercase A, lowercase a, and exclamation mark. Now it's complaining about password length. Let me set it to 1357924, uppercase A, lowercase a, exclamation mark. Success. By enforcing strong password, we significantly reduce the risk of unauthorized access to the account and also increase the amount of time needed to crack it. Aim for at least 12 to 14 characters. Another important security factor is password history. It's a feature that stores a record of users' past passwords. Its main goal is to discourage users from reusing the same password after changing it. It also forces users to create somewhat more diverse passwords. To set it up, let's open Common Passwords PAM configuration file and let's add Password History module. By setting remember equals 3 for the module, it remembers the last 3 passwords used. Use out token option tells the module to use the password provided by previously stacked authentication module. Let's try changing the password. I will provide the old password. Now, let's generate a random 10 characters password and let's set it as the new password. Let's change the password again. I will try to put the 1357924 capital A, lowercase a, exclamation mark. That's the password we had in the first place. It tells me that I cannot use this password as it has been already used. Password history is kept in O passwd in etc security. Password history can be a helpful security tool, but it's not a silver bullet. The final aspect I'd like to highlight is password aging. With this technique, passwords have an expiry date, prompting users to change them periodically for enhanced security. Enforcing password aging reduces the window of opportunity for attackers to exploit it. Password aging is defined in login defs configuration file. There's the maximum number of days a password is valid. Let's set it to 30. Then there's the minimum number of days a password needs to be used and cannot be changed. Let's set it to 1. Basically, if you change a password, you need to wait 1 day to change it again. Lastly, there's the password warning. You'll be notified about the need to change the password 7 days prior to password expiry. Unfortunately, those values are taken into consideration during account creation. To modify values for existing user, let's run the change age command. Let's set the minimum password age to 1 day, so you cannot change your password more frequently than once per day. Let's set the maximum password age to 30 days. In other words, you will need to change the password at least every 30 days. The password inactive period serves as a grace period during which you can still log in, but you are required to change your password. If the grace period expires, your account will be locked. Let's try changing the password. As the minimum password age is 1 day, we need to wait longer to change it. Let's change the minimum password age back to 0, so we can change the password as frequently as we want. I will set the maximum password age to 7 days and expiration warning to 8 days. Let's try switching to the test user. This time, we've received an expiration warning indicating that our password is set to expire in just 7 days. You can list all those password-related parameters and dates with change age-L. Implementing measures such as enforcing strong passwords, frequent password changes, and account locking is crucial for enhancing our system security. These steps serve as the foundation of system hardening, fortifying our defenses against cyber threats. They not only safeguard our personal data, but also protect our businesses and critical infrastructure from potential cyber attacks. However, it's essential to acknowledge that while passwords offer a level of security, replacing them with keys and implementing multi-factor authentication significantly bolsters our defenses against sophisticated attacks. Rest assured, we're continually progressing towards stronger security measures. Despite the presence of firewalls and robust system architecture, passwords remain a potential vulnerability that cannot be overlooked. In our next discussion, we'll delve into controlling root account access, securing SSH service, and underscore the importance of firewalls in maintaining a secure system. If you found this video informative, please consider giving it a thumbs up and subscribing for more engaging cybersecurity content.